Welcome to today's Masterclass. To start with, there's an activity for you to work on. Can you use the Bridges of Konigsberg map provided to draw a single path that crosses all 7 bridges without crossing the same bridge twice? If you get stuck, try starting it from a different place. Pause the video to have a go. How did you get on? In this masterclass session, we'll be thinking about drawing paths and looking at how things are connected together. You've been trying to draw a path through this city. Has anyone managed to do this, following all the rules? I know that nobody will have said yes to that, and this is interesting. As mathematicians, we see this kind of thing happen and think, maybe there's a reason for it. So, we're going to learn some ways to work on problems like these and to understand them better. The diagram that you were looking at is based on a real city, the city of Konigsberg, which used to be in Germany, but it's now part of Russia, and it's changed its name as well to Kaliningrad. A mathematician called Leonhard Euler used to live in St. Petersburg nearby, and someone asked for his help to solve the problem. If you live in this city, can you travel around and visit all 7 bridges? This is a picture of the actual city, but the sheet we've given you has a much simpler version of this picture, just like the one shown on screen now. To solve this problem, we don't need all the extra information about where the houses are and how many boats are in the river. So this version of the picture just shows the rivers and the bridges. When Euler worked on this problem, he used an even simpler version of this picture, which looked like this, the one on the screen now. It doesn't even show the shape of the river or the layout of the bridges, but just the way the 4 sections of land are connected. Can you see that these 2 diagrams represent the same layout? Which section of land does the point on the left represent? Yep, it's the central piece in the middle of the river, because it has 5 bridges connecting it to the other pieces of land. So now, instead of asking the question, can you find a route that crosses all the bridges, the question can now be, can you find a route that travels along all these lines? Which is the same as saying, can you draw this shape without taking your pen off the paper and without going over the same line twice? The way that Euler found a solution to the problem was to look at other examples of similar problems to see if he could figure out what makes it possible to draw these shapes. We've got a sheet of examples for you to try here. For each of these diagrams, try to draw the whole shape with one line without repeating any sections, which means not going over the same line twice, and mark in the table at the bottom whether you think it can be done. Pause the video now to have a go. Don't give up too quickly. How did you get on? This slide shows one possible solution to each of these paths, but the second one is not possible. The diagrams we've been tracing here are examples of what mathematicians call graphs. Not the kind of graphs you might have studied before, with axes and a plot or bars, but graphs which are networks of points. Here's some new words you'll need to know about graphs. Vertex. This is the word we use to describe a point, one of the dots that makes up the graph and is connected to the other dots. Edge. This is the word we'll use to mean one of the lines that's connecting 2 points. Graph. This is the word for the whole shape. It has to be connected in one piece, and every edge has to start and finish at a vertex. That's very important to remember. Euler path. This is what we've been trying to find. It's a path that starts somewhere in the graph and goes along each edge, so each line, exactly once. If you can find an Euler path, that's the same as saying you can draw the graph without taking your pen off or repeating and going back on the same line. Here are some examples of things which are not proper graphs. Can you think why and how we can fix each of them? Let's start with the one in the top right. It's got an edge that crosses here without a vertex at that point, which means all these edges meeting in the middle don't have a vertex at both ends. How could we fix that? We could add a vertex here, or we could just move this vertex and edge down to stop it from crossing the other one. Is that okay now? Yep. Okay, what about this one in the bottom left? It's missing some vertices, so it means we've got some lines without the dots there. We can't fix it by moving the edges, but we could add 2 vertices. This one in the top left corner has an extra edge here with no vertex at the end, which means no dot at the end. So we could fix it by adding a vertex at the end or removing that edge. Now, I'd like you all to design your own graph. Remember all these rules. You can't have the end of an edge or 2 edges crossing without a vertex there, and it has to be one connected piece. When you've finished, write down how many edges and vertices you have in your graph. Pause the video now and have a go. How did you get on? One way that Euler used to understand graphs better was to look at each vertex and count how many edges meet there. For example, in these examples of graphs we've been looking at, these points have one edge. I've labelled them on the screen. These points have 2 edges coming from them. And then these ones all have 3. Euler also thought it was important to know whether the number of edges meeting at a vertex is odd or even. So even whether it's divisible by 2. I've used a different colour to mark which of these are odd numbers and which of these are even. So even being black and odd being my sort of like bluey greeny colour. For each graph, count how many edges meet at each corner and label them in 2 different colours for odd and even, just like I did. And now fill in the table that we provided for you. These are the same graphs from the previous sheet, so we know whether they're possible or not. Copy that information across into this table. See if you can find a pattern. Pause the video to have a go. How did you get on? Did you spot a pattern? If you filled in the whole table, it should look like this. Can anyone see a pattern in this table? If your graph has 2 odd vertices, it can be done. And if it has 0 odd vertices, it can also be done. But if it has 4 odd vertices, it can't be done. This isn't just a pattern. It's always true for any graph that if it has 2 or 0 odd vertices, it has an Euler path. It can be drawn. And if it hasn't, then it can't. Take some time to think about why this might be true, and discuss it with the people nearby. Look at the paths you've managed to draw on the ones which are possible, and where the vertices are. Think about what happens when you pass through a vertex. You might have noticed that when you pass through a vertex, you go in along one edge and out along another. So that uses 2 of the edges from that point. That means if there's an odd number of edges, you can use up all but one of them by going in and out. The only way to use up the remaining edge is if you start or finish at that vertex. Then that edge is the first or the last edge that gets used. This means if there are exactly 2 odd vertices, there will be the start and finish of your Euler path. If you didn't already notice this, check your paths now and see that you always start and finish at the odd vertices. If all the vertices are even, you can still draw an Euler path, but it doesn't matter where you start and finish. You can even start and finish in the same place. Now we can look back at the bridges of Konigsberg graph and see that this has 4 odd vertices, which means it's not possible. If you couldn't do it, you shouldn't feel bad, because it can't be done. In fact, by understanding the reasons why it can't be done, we've solved the problem. This was the answer that Euler came to after all his work. But at the same time, he'd also managed to work out this way of understanding graphs, and he hadn't just solved the problem for this graph, but for all graphs at once. One other way Euler used to study graphs was to count how many edges and vertices they have, and also how many faces. When I say faces, I mean regions, areas of space closed off by the edges, including the one region outside the whole graph. So here are some examples of the numbers of vertices, edges, and faces for each of these graphs. Euler came up with a formula which connects these 3 numbers, and it was to take the number of vertices, V, minus the number of edges, E, plus the number of faces, F. So we're going to work this out for all the graphs on our sheet and some new ones. Use this sheet, the Euler Formula worksheet, to write down V, E and F, and V, take away E, add F, for all the graphs on the first sheet, which I've also put up on the screen, and for these 4 new ones. Now you've filled in this table, you should find a pattern in the numbers. Can you spot what the pattern is? It looks like V take away E add F is always equal to 2. This is the pattern that Euler found, and it will always work as long as your graph is correct. To understand why, we can start with a very simple graph. If we just have one vertex, V is 1, and F, the outside region, is also 1. What's V take away E add F? So we've got one vertex, take away 0 edges, no lines drawn, add 1 equals 2. Now we can add one edge. And there are a few ways to do this. We could add an edge from this vertex back to itself. If we do this, we have one edge now, but also one extra face, as we've closed in a region. So we've got inside the circle and outside the circle. So what's V take away E add F this time? Well, we've got one vertex, one dot, take away one edge, which we put in, and now we've got 2 faces. So 1 take away 1 add 2 equals 2. So if instead of adding an edge that joins back to the same vertex, we add one that doesn't, we'll need an extra vertex on the end of it. Here we go. So we've got an extra vertex and we've got an edge there. We could do this. Now, what's V take away E add F? So we've got 2 vertices, 2 dots, take away one edge, one line between them. And how many faces have we got here? Well, we've only got one region, haven't we? Because nothing's enclosed by the edges. So we've got 2 take away 1 is 1, add on 1 is 2. If I want to just add an extra vertex, I could do that by adding 1 here in the middle of an edge. But now instead of 1 edge, this is 2 edges. So what's V take away E add F now? Well, we've got 3 vertex, 3 dots, take away 2 edges, And then, we've still only got one face because nothing's enclosed by any of those edges. So we've got 3 take away 2 is 1, add on 1 is 2 again. And finally, if I want to add a face, a closed region, I could do that by adding an edge like this that goes from this vertex to this one and closes off this face. So what's V take away E add F now? Well, I've got 3 vertex, 3 circle dots. Take away 3 edges, 3 lines linking those dots together. And then I've got 2 faces now because I've got the whole outside space and then I've got an inside space created by 2 edges there. So this will always work. You might be thinking that you already know the words vertex, edge and face from somewhere else. Can you suggest what else has vertices, edges and faces? Have a think. Yeah, you may have heard these words when talking about 3D shapes, like this cube or this prism. And this formula of Euler's also works for simple shapes like these. How many edges does a cube have? How many vertices? How many faces? And what's V take away E add F? What about for the prism? Pause the video and have a go. One final thing before we finish. Now we understand how to make a graph which does have an Euler path. I want you to redesign this city. The islands will be the same shape, but you can draw in your own bridges. I want you to do this so that this city does have an Euler path in it. So you can cross all bridges in one journey and not go over the same bridge twice. You do need to be able to get to all the parts of the city though. You can also give your made-up city a name and draw in some other famous made-up landmarks that someone who follows the Euler path might visit. Remember what the rules are for something to have an Euler path? Only 2 or 0 odd vertices. If it helps, you can draw the graph first on another piece of paper and then put in the bridges on the map. We've also learned in this session about graphs and what an Euler path is. And we also know Euler's formula, which works for graphs like these and for simple shapes in 3D as well. Now you can challenge your friend to draw shapes like these, and if they get stuck, you could tell them to count the edges of each vertex. And if you find any new 3D shapes, check if they also work with Euler's formula by counting the vertices, edges and faces. If you've enjoyed today's session, these are activities that you can try at home from the Enrich website, starting with the tourism problem. Then we have the Konigsberg plus problems, where you can experiment further with different numbers of islands and bridges. There's also the Who's Who problem, where you can represent a group of friends by drawing a graph similar to the one we've done today. Or even the rail network problem for those people who are aspiring to be rail designers out there. And that's the end of our masterclass. Thank you for all of you who took the time to join me. I hope you've enjoyed it and you've learned something new. See you soon.